Alright, this is Steve Earth here, and we're going to continue our calculus study of trying to find volumes of solids. And this time what we're going to do is, rather than do a solid of revolution, we're going to do something where you have cross-sections stacked up on a base. So let's take a look at an example of this. I'm going to use Sketchpad again because it's really good at doing three-dimensional pictures. So we're going to start with a circle of radius r, and just centering it at the origin right here. And right now we're just in the xy plane. We don't have a solid yet. So in order to create a solid, we're going to think of this as being a base, and we're going to stack some equilateral triangles on top of this circle. And what we're going to do is, imagine we're going to be chopping up the x-axis right here with little slices. So actually I'm going to start off with that. And this is a sketch, again, written by Audrey Weeks, and she has it sort of broken down to parts. So our first part is, hey, let's show these chords. Let's take a look at these slices right here. So on each one of these slices, we're going to stick up, kind of poking out at us, an equilateral triangle. So now in order to see this, we have to look at it in an angle, because it could be sticking up at us right now for all we know, and we wouldn't really see it. So she has a button here which says, hey, let's tilt this down. Okay, so this is, I know it doesn't really technically look like a circle anymore, it looks like an ellipse, but this is just supposed to be perspective, right? So now it's kind of rotated down, and let's stick on, she has a button here that lets you put on 4 equilateral triangles. Now really there's an infinite number of equilateral triangles stacked up here, but she just picked out 4 for us to look at. So there's 4 of them. So here's the black one, it's kind of close to the edge, so it's kind of tiny, and as these move closer and closer to the diameter of the circle, these are getting bigger and bigger and bigger. And if you want to see it rotated back towards us again, this is it rotated back, this is it rotated there, so we can kind of see the triangles. Now, just to show you there's actually an infinite number of triangles here, she has something called a sweep, so let's push this button so you can kind of see, here's this triangle. Every single time she takes a slice on one of these chords, you're creating an equilateral triangle. I know it doesn't quite look equilateral, but that's just because of the angle. And I can actually rotate this while that's going by, and you can kind of see what's going on there. Alright, now if you imagine this triangle kind of staying there as it goes, these are different cross-sections as we chop up the x-axis. So let's actually take a look at the solid. So we're going to make the triangle actually keep the image as it moves. So now it's not erasing it as it goes. It's just keeping all these different triangles on there. And now you can kind of see what's going on there. So let's actually take a look at the entire solid. And it might not be exactly what you imagine. A lot of people just say if you stack up a whole lot of equilateral triangles on a circle like this, you know, they're not necessarily going to guess what this shape is. Let's take a look at this shape. So it looks a little bit like a shark fin kind of, or sort of a pinched bowl where you've got this ridge going down the middle. I'm going to rotate it again so you can look at it from different angles. Pause it for a second. So there it is right there. You can see the different triangles. In fact, let's actually take a look at some of the triangles in here. So those are those 4 original triangles, and you can see they're kind of making up the solid. And let's actually see it sliding through the entire solid there. So those are all the different cross-sections of the triangles making up this kind of shark fin. And our question that is for us now is, what is the volume of this shape? So we're going to have to use calculus to find that out. Alright, so our plan is to try to be able to find the volume of this crazy shape. So remember, we've got a circle of radius 2 right here, and perpendicular to the x-axis and sticking out of the plane right here are these equilateral triangles. And our goal is to add up all the areas of these triangles, and that would give us the volume. So let's begin by drawing ourselves a circle. So I'm kind of looking at it from the top down. So the equation of our circle is x squared plus y squared equals 4. And let's just take a slice right here at x. And keep in mind that means that this spot right here, this length is y. Think of this as the this point is x comma y, so we went x across and y up. So we know we have sort of triangles sticking up out at us here. It's a little bit hard to see, but it kind of goes like that. And let's kind of maybe redraw it over here. I think it might be a little bit easier. So this section right here, which is y, that corresponds to that. So this yellow dot right here, that's this yellow dot on the axis. And this is the triangle that's sticking up at us over here. So we have to use the formula for the area of a triangle, which is half base times height. Of course, we still need to figure out, well, what is this height? And there's a few ways to do that. Probably the easiest way is just to realize that, well, this entire length right here is 2y. But this is an equilateral triangle, so this is also 2y. And this part right here, we could either just use the Pythagorean theorem, or we could have actually just used the tangent of pi 6. But this right here is y root 3. So coming over here to get the area, it's 1/2 the base. Remember, the base is all of this, so it's 2y, times the height, which we just figured out is y root 3. And we can notice here those 2's are just going to cancel, and y times y is y squared, so it's just y squared root 3. Now, keep in mind, though, we're going to be chopping up the x-axis. So this all needs to be in terms of x. So we don't want to leave it as y squared root 3, but we know that y is actually equal to the square root of 4 minus x squared. I just kind of rewrote this part right here. So rather than thinking of it as y squared root 3, well, y is just this. When you square it, the square root goes away. So it's just 4 minus x squared root 3. So what that's telling us is the area of this triangle in terms of x. So in other words, it depends where you take your slice. So if I take my slice right here at this diameter, that means the x is 0. So that means you got the biggest triangle possible. So if x is 0, the area of the triangle is 4 root 3. On the other hand, if we take it at the very, very tip, so this right here would be x equals 2, because the radius of this circle is 2. Notice if you plug in 2 in for x, 2 squared is 4, 4 minus 4 is 0, 0 root 3 is 0. So it's saying that at this very tip, the area of the triangle is 0, which makes sense, because when you chop it right there, there's really not a triangle there, it's just a single point. So, alright, my page is getting kind of full, so I'm going to do my little shrinky-dink trick again. So just stick everything we just did up there, because now at this stage we're ready to actually find the volume. Once you get the formula for the area of the cross-section, all you have to do is add it all up using integration. So our volume is going to be the integral from -2 to 2, because we start at -2, go to 2, that's where we start our chopping, of the area formula. Notice, by the way, there's no pi, right? Pi is what you get when you're doing solids of revolution. But here, there's nothing spinning, there's no circles involved necessarily, it's all just adding up these triangles. Now, the root 3, that's just a constant, so I might as well just pull that outside the integral sign. And at this stage, it's just easy peasy lemon squeezy integral. So integral of 4 is 4x. The integral of x squared is... Oops, I just noticed I made a boo-boo. Alright, sorry about that little retro bat play action there. So I don't know if you guys noticed, but I'd forgotten to put the cube on there. But I went ahead and fixed that. So, yep, so first we got a little stick here. So after we integrate x squared, that becomes 1/3 x cubed. I accidentally left off the cube there, but I kind of stuck it in. So first you stick in 2, so that's 8 minus 8/3. Then subtract what you get when you plug in -2, which would be -8 plus 8/3. And yeah, then I just did the arithmetic, so that becomes a plus 8. 8 plus 8 is 16. And here you have a minus 8/3. Here's another minus 8/3. That's minus 16/3. Put it all together, 32/3, with a radical 3 out in front. So that's it. That is the volume of a shape in cubic units.